This is the standard level paper 2, May 2011, time zone 2 paper. And we're going to be starting off with question A1, which is always a data analysis question. So the speed v of waves on the surface of deep water depends only on the wavelength of the waves. The data gathered from a particular region in the Atlantic Ocean are plotted below. The uncertainty in the speed v is plus minus 0.3 meters per second, and the uncertainty of lambda is too small to be shown on the diagram. So state with reference to the graph why v is not directly proportional to lambda, and we also need to find what v is for lambda is equal to 39 meters. So let's go back to our graph and we can discuss that. So they're asking now, why is v directly proportional to lambda? Now for that to occur, you need the graph to go through the origin, and it needs to be a straight line. So clearly you can't put a straight line going through all the error bars. That will also go through the origin and also go through all the error bars. For 39, they also want to know what the velocity is when your wavelength is 39. Now, you've just always got to be careful with the scale. 39 is over here. And so if I go up here, it's going to be over there. And you can see they've actually drawn you where that line is. So giving you a helping hand there. And when you do it, it's over there. So it's important here. Obviously, you're going 5 small blocks from 7 to 8. So that's in the mid between there. So that's going to be 7.7. So 7.7 meters per second is when your wavelength is equal to 39 meters. Okay, so those are those two questions. Going on here, it is suggested that the relationship between v and lambda is v is equal to a square root of lambda, where a is a constant. To test the validity of this hypothesis, values of v squared against lambda are plotted below. So in looking at this, we've got, if we have v squared, that would equal a squared lambda. And if I plot v squared, we could say call that y, and your lambda, that is x. That indeed would be in the form y is equal to some constant kx, or a proportional graph. So trying to put that in a proportional graph. So it says use your answer to A2 to show that the absolute uncertainty in v squared for a wavelength of 39 is equal to plus minus 5 meters squared s to the minus 2. Now, we're going to use this formula over here, that we have v squared obviously is equal to v times v. So we know that the error in v, it was given as 0.3 meters per second to negative 1. So using the formula, that your absolute error in v squared divided by v squared would actually equal delta v over v plus delta v over v. We could then multiply the whole thing through by v squared, and we would get that. So we would plot this in, we'll get delta v squared. The error in v squared is 0.3 over 7.7 plus 0.3 over 7.7 times 7.7 squared. And when we do that, we get a value of about 4.6 meters squared s to the minus 2 squared, because this is obviously a squared value. And that's plus minus, that becomes your plus minus 5 when you do it in to one significant figure. All right. Now I'm just going to have to change my view here, because to put this in, actually, well, it's over here, so this is all right. It says the absolute uncertainty of v squared for a wavelength of 2.5 meters is plus minus 1 meter squared s to the minus 2, and we've just worked it out there for v squared for 39 meters is 2.5. 0.4 lambda is 2.5, and 39, we've worked this one out, was plus minus, as it says over here, 5 meters squared s to the minus 2. So we have to plot those up. So let's just go back here. No, not there. Over here. So we want it for 2.5. So this over here would be my 2.5. So now we got plus minus 1 meter. Now here each of these is 2. We've got 2, 4, 6, 8, 10. So 1 would actually be a half. So we've got to draw on either side. Now it's not easy for me to do it because I can't get so accurate. But basically you've got half a block on either side like that. For the 5, that's obviously going to be 2.5 blocks, because each one is 2, so this is going to be 2.5 blocks, and this is for 39. So here we are going for 39, that one over there for 39 meters, this one over here, so that's going to be 2.5 blocks on either side. So just make sure that you've got it right, 2.5. Mine aren't actually right, but so it's going to be 2.5 on either side there. Hope that's reasonably clear. So state why the plotted data in B2 suggests that it is likely that V is proportional to lambda, and use the graph opposite to determine the constant A. We're going to do it, and then we've got to put it into there. So firstly we want to find out, show that this is probably true, this hypothesis, and work out that constant A. So going back here, so when looking at this, it seems like you can draw a line from your origin, a straight line, that goes through those points. So because a straight line going through the origin goes through those points, it is likely that this hypothesis has some value. You do have this point over here, but that could be an outlier, but generally that would be true. Then we want to find our value for A. Now we have got V squared is equal to, it would be A squared lambda. So this A squared is the slope of this graph, is equal to the slope for this graph over here. So in doing this, let me just try to redraw this line a little bit more accurately. I think it will go sort of like through there. Something like that. Now, when you're finding the slope from a graph, you always try and use as much of the line as possible. So I'm going to use the full amount here. I'm going to go all the way there, like that, and all the way across, like that. So when I'm finding the slope, which is going to be A squared, so A squared is going to equal that amount there, which is my change in V squared. That is going to be 70. And when this over here is 45. So A squared is equal to 70 divided by 45. I'll just do it on my calculator here. 70 divided by 45. And you get about 1.55. But remember, A is going to be the square root of that. So we can just put it in like that if we want to find what A is. So we take the square root of that value, and we get about 1.24. So we can say A is equal to 1.2 because all these values are given in 2 significant numbers. So I'm going to give mine in 2 significant figures like that. Now, so you've got your slope is equal to that. Your A value is equal to that. Your units for this, obviously here we're going to have, this is meters squared s to the minus 2 divided by meters. So that cancels with that. And then we take the square root of this. So this is actually m to the half s to the minus 1 is going to be your units for your slope. Going on to this one over here, now we have got that as a, so a is 1.2 is equal to k, the square root of k over 2 pi. Obviously we're going to square that, and then we're going to multiply it by 2 pi will give us our k value, what our k value is. So k will equal 2 pi times 1.2 squared, and we should be getting a k value there of about 9.4 meters per second to the minus 2 is our value there. Okay, so that was that question.